Hi, welcome to the Olympiad geometry. Let's continue our study on the geometry triad. Before we start, if you think this video is helpful, please click the like button, comment, share, and subscribe to the channel. So today we're going to talk about the conjugate median. In the previous several videos, we talked about the generalization of the angle bisector theorem. We talked about the harmonic bundle, and we talked about the Michel's point, and all of those are the fundamental of the conjugate median. So let's just learn about the definition of the conjugate median first. A median is defined by a vertex of a triangle and its opposite side midpoint, right? So if we have a triangle, let's call it A, B, C here. Right, we have this triangle ABC here, and we find the midpoint of BC. And we connect the vertex A to the midpoint of the opposite edge BC, which is M. So we call this AM as a median for the triangle ABC. The symmetrical line of the median to the angle bisector of the vertex angle is called conjugate median, which means we find the, this figure is not that clear. Let's make another one here, right? So this is easier to check. For example, this is median. This is a midpoint. We connect AM, which is a median of the triangle ABC, and we find the angle bisector here. Which is, let's call it AD, right? AD is the angle bisector. And we find the symmetrical line of the AM to AD, which is this line here. Let's call it, for example, T, right? AT. Then we call AT as conjugate median, right? So here we need to demonstrate one thing. What is the symmetrical line of one line to another? Assume you have one line here, let's call it L. And we have another one line here, L1. What is the symmetrical line of the L1 to L? It's just we have the, except this intersection point, every other point on the symmetrical line would be on the opposite side of the line L comparing to the L1, right? And also the angle formed by L1 prime, which is considered as a symmetrical line of L1 to L, should form the same angle with line L as L1, right? So here is theta, this is theta prime, and theta equals to theta prime, right? That's a symmetrical line. So now we know we have a median here, we have the angle bisector AD here, then we just find the equal angle of MAD that equals to angle DAT. Then we know that AT is a conjugate median. That's the definition, we just accept it. Okay, that's for the first definition, and let's look at the second one. Definition 2. The line passing through a vertex of a triangle and in parallel with the opposite side is called external median. Okay, this is a little more difficult to understand. Basically, it's saying that we have a line passing through a vertex and in parallel with the opposite edge, which means that we find a line that passing through A and in parallel with BC, right? this line passing through A and in parallel with BC. This line is called external median. Now the question is that why we can call it a median, right? I know here we give the definition as this one, right? But we have to come up with some reasons that we can give this definition. We cannot force a definition on it. So think about the problem like this. Think about that how we get the median. We basically find a point on the segment BC, which we can say that we find a point on the line BC, but inside with the segment BC, right? So that BM to MC equals to 1, right? We find this point M. It has a property that BM to MC equals to 1. And then we connect AM. We call AM to be the median. And that's the case, M is inside of segment BC. Let's consider another case that M is out of the segment BC, right? So if M is out of segment BC, then we can see that BM to MC, for example, M is on the right side of the BC, right? So M is here. Then BM to MC is always equal to BM plus BC to MC. Sorry, here should be CM. CM plus BC, which is BM, divided by MC. And we want to force it equals to 1, which means M is on the infinite far away point, right? Infinite far away point, which eventually we have this one equals to 1, right? M is infinite far away from BC. And now we want to connect AM. We want to connect AM, which means the line AM meets line BC at the infinite far away point, right? Which means AM is in parallel with BC, right? And it still satisfies that that still satisfies that BM to MC equals to 1. Okay, so that's the reason we call it external median. Now we look at the second half of this definition. So we already know that the line passing through a vertex of a triangle and in parallel with the opposite side is called external median. The connection of the vertex and the midpoint of the opposite side extension, which is infinite far away from the vertex, which is in parallel to the opposite side, right? That's what we just explained. And the intersection point of the two external median is called eccentroid of the triangle. So that is saying we find a parallel line that are passing through A to BC, and we find another parallel line passing through B to AC, right? This point would be called external centroid or eccentroid. So for a triangle, we should have 3 eccentroid here, right? We will discuss about this later, but let's look at the definition 3. Definition 3 is saying that a symmetrical line of an external median to the vertex angle bisector of this vertex is called conjugate external median, right? It's easier to understand when you understand the conjugate median, right? Basically, conjugate median is saying that we find the median first, we find the angle bisector here, and we just find the symmetrical line from the median to the angle bisector line. We got the conjugate median. And for here, we already have external median here, and we find the angle bisector line here, which is AD, this point, right? We find AD here, and we find the symmetrical line of the, let's call it AN, the AN to AD, which is this line. Let's say it meets BC on another point, for example, call Q. Then AQ would be the conjugate external median, right? It's conjugate to the external median. And it's a tangent line of the circumcircle of the triangle as this vertex. I'll explain this later. And into conjugate external median intersects point is called conjugate external centroid. We know the external centroid, right, or x-centroid. And now we have another term called a conjugate x-centroid. Okay, that's a whole definition. Let's just study about this a little bit more. So we have a triangle here. And think about we want to find the circumcenter of this triangle, which is roughly say here, right? Because this is a perpendicular bisector intersection point. So let's call it O, and we have A, B, C here. And we know that the line passing through the A and in parallel with BC is called, let's call it AN. This is external median, right? We have the external median, and we want to find the conjugate external median, which is we find the angle bisector of angle A first. Let's call this to be D, right? Which means we can also, which means we have this angle, right? The angle NAD equals to another angle, right? And for this line here, call it E. Then AE is conjugate external median, right? AE is conjugate external median. Okay, now it's basically saying that the conjugate external median is a tangent line of the circumcircle of triangle ABC, which means if it's true, then OA should be perpendicular with AE. Okay, we want to prove that. Now, if we connect OA and connect OB, we know that angle BOA equals to twice of angle C, right? Here, angle C means angle BCA, which means angle OAB equals to 180 degree minus angle BOA and divided by 2, which is 90 degree minus angle C, right? That is angle OAB. So what about the angle OAE? The angle OAE equals to angle NAE minus angle NAO, right? Angle NAE minus angle NAO, that is angle OAE. So it equals to angle NAE is twice of angle NAO. twice of angle NAO minus angle, twice of angle NAD, right? Twice of angle NAD, that is angle NAE, minus angle NAO. Okay, what is angle NAD? NAD, because NA is in parallel with BC, so angle NAD equals to this one, the angle ADC, right? And we know that angle ADC, that's twice of angle ADC minus angle NAO. So let me write it down here. The angle OAE equals to twice of angle ADC minus angle NAO. And angle ADC equals to angle B plus half of angle A. So it equals to twice of angle B plus angle A minus angle NAO, right? And angle NAO equals to angle NAB, which is angle B, plus angle BAO, which is 90 degrees minus angle C. So let's expand this one. We get angle B plus angle A plus angle C minus 90 degrees, which equals to 180 degrees minus 90 degrees equals to 90 degrees. Right, that means angle OAE is 90 degrees, OA is perpendicular to AE, which means AE is the tangent line of the circumcircle of the triangle ABC. Okay. So here, it's a tangent line. It's a tangent line of the circumcircle of the triangle at this vertex, right? And then the next thing is very easy to understand. Any two conjugate external median intersection point is called conjugate external centroid or conjugate X centroid. Okay, it's just relative to the X centroid. Okay, now we look at here the properties of the conjugate median. See the first one here, the theorem one. In the triangle ABC, D is on BC, E is on extension of side BC. Then AD is a conjugate median if and only if AB squared to AC squared equals to BD to DC, right? Let me repeat this again. In the triangle ABC, D is on BC. D is on BC, E is on extension of the side BC, then AD is a conjugate median if and only if BD to DC equals to this one. So let's just think about the first case that we already know the here. This is D point. Now that I set the angle bisector as AT, I set the midpoint as M, right? Basically, we say that we already know AD is a conjugate median. I want to prove that BD to DC equals to AB squared to AC squared, right? So if you remember that when we discuss about the generalization of the angle bisector theorem, we talked about one theorem, is that Steiner theorem, which is saying that in a triangle ABC here, again, I strongly recommend you, the audience, if you haven't watched the video that I talk about the generalization of the angle bisector theorem, the harmonic bundle, and the Mikos point, I strongly recommend you to watch those videos first, right? That's the basic of this. This is a higher, advanced topic of that. So let's call it D1 and D2. That's a 2-point on the side BC, right? If we connect AD1, if we connect AD2, and we found that angle BAD1 equals to angle D2AC, right? These two angles are equal. Then we know that BD2 to D2C times BD1 to D1C equals to AB squared to AC squared. Right? That's Steiner's theorem we discussed about. So let's just apply it here. Because AT is angle bisector of angle BAC. Right? So we know that angle BAT equals to angle TAC. And because AD is symmetrical to AM on AT, right? That means angle MAT equals to angle TAD. Based on these two, we know that angle BAM equals to angle DAC, right? BAM equals to angle DAC, which means we can use the Steiner's theorem. That is saying, we have the point M and D on the side BC, which forms that BAM equals to angle DAC, right? So BM to MC times BD to DC equals to AB squared to AC squared. That's the Steiner's theorem. And we know that M is the midpoint of the segment BC, so BM equals to MC, which means BD to DC equals to AB squared to AC squared. Right? And we already proved before that on a segment, if you fix a ratio, then this point is fixed. So we basically proved the case that if and only if, right? That's for the conjugate medium. And for the external conjugate medium, it's similar here. So for the external conjugate medium, we want to prove, or we want to find the ratio of BE to EC. We want to prove that BE to EC equals to AB squared to AC squared, right? Remember that how, let's write it in here, how we find the AE if, so let's say if AE is external, is conjugate external medium, right? If AE is a conjugate external medium, that means the angle NAT equals to angle TAE, right? And we want to find the ratios at BE to EC. BE to EC equals to the area of the triangle BAE to the area of the triangle CAE, which equals to half of AB times AE times sine angle BAE, right? Divided by half of AC times AE times sine angle CAE. Right, so which equals to AB to AC times sine angle BAE to sine angle CAE. Right, so the angle CAE equals to CAE equals to angle TAE minus half of angle A. Right, so the angle CAE equals to angle TAE minus half of angle A, right? Angle CAE equals to angle TAE minus angle TAC. That is angle TAE minus half of angle A. And we know that angle TAE equals to angle NAT, right? Angle TAE equals to angle NAT. And for angle BAE, that is angle TAE plus half of angle BAC, half of angle A. So angle TAE plus half of angle A. So again, what is angle NAT or angle TAE? Angle NAT equals to angle ATC, right? So angle NAT equals to angle ATC, which is angle B plus half of angle A, right? That means the angle CAE equals to this one minus half of angle A, so that equals to angle B. And angle BAE, that is angle B plus angle A, which is 180 degree minus angle C. Right? So let's look at the sine angle BAE, which is the sine angle 180 degree minus angle C, which is sine angle C, right? So it equals to AB to AC times sine angle BAE is sine angle C, and sine angle CAE is sine angle B, right? So sine angle C to sine angle B, which is AB to AC. So it equals to AB squared to AC squared. Okay. That is first property. And based on this property, right, we know that BD to DC equals to AB squared to AC squared. And we know that BE to CE equals to AB squared to AC squared. So for vertex of a triangle, the conjugate median, which is AD here, the conjugate median, external conjugate median, which is AE here. Two sides passing through this vertex, which is AB and AC, form a harmonic bundle, which is obvious, right? Because BD to DC equals to BE to EC equals to AB squared to AC squared. So that's a harmonic bundle. Any circle passing through this vertex intersects these four lines on 4 points, which form a harmonic quadrilateral. Okay, so it's basically saying that if we draw a circle here, let me draw a small circle here. This circle is passing through this point A, and it has 4 intersection points here, right? We have this one, this one, this one, and this one here. So we have these 4 points here, and it's saying that these form a harmonic quadrilateral. Actually, this is a property that we discussed in the harmonic bundle, but we can prove it here again. So what we really want to do is to prove that this is a harmonic quadrilateral, which let's give it some name here. P, Q, S, R. Okay, so we want to prove that PQSR is a harmonic quadrilateral, which means we want to prove that PQ times RS equals to PR times QS, right? And PQ can be rewritten as 2R sine angle BAQ, right? Times RS. RS can be written as 2R times sine angle SAR, right? And what about QS? Here, PR can be rewritten as 2R sine angle PAR. And the QS is 2R sine angle QAS. Right? Basically, we want to prove this. Okay, let me rephrase this one here. For the first thing, the sine angle BAQ or sine angle PAQ, which is sine angle BAD, right? Basically, we want to prove that the sine angle BAD times sine angle SAR, which is CAE, sine angle CAE, equals to sine angle PAR, which is sine angle BAE, times this one, sine angle QAS, which is sine angle DAC. Right. So for this one, we can rewritten it as we want to prove AB times AD, half of AB times AD times sine angle BAD times AC times AE. So half of AC times AE times sine angle CAE. We want to prove this is true, right? We want to prove this is true. So it equals to, we want to prove, it's equivalent to this one, that I write it down as a half of BAE, which is AB times AE times sine angle BAE times half of DAC, which is AD times AC times sine angle DAC. Right. So we basically change this one to this one. On the both sides, we times AB, AD, half of AB, AD, half of AC, AE. Here it's AB, AD, AC, AE, right? And now we look at this one. The half of ABAD times sine angle BAD. ABAD sine angle BAD, which is the area of triangle BAD. And ACAE sine angle CAE, that's the area of triangle CAE. Right? And here we have ABAE times sine angle BAE, which is the area of triangle BAE. Similarly, we have this one, which is the area of triangle DAC, right? And for this one, so basically we want to prove that the area of triangle BAD to the area of triangle DAC equals to the area of triangle BAE to the area of triangle CAE, right? These two are equivalent. And the area of triangle BAD to the area of triangle DAC, BAD to DAC, that is BD to DC, right? That is BD to DC. And the area of triangle BAE to the area of triangle CAE, that is BE to CE. Basically, we want to prove this one. And this is obvious, right? Because they all equals to AB squared to AC squared. Right? All of these steps are reversible, which means we just proved that any circle passing through this vertex intersects these four lines on 4 points, which form a harmonic quadrilateral. Okay, that's conclusion 1. And let's look at theorem 2. In acute triangle ABC, D is on side BC, point KA is a conjugate accentroid that opposite to the vertex A. Then AD is the conjugate median if and only if ADKA are collinear. Right, this is kind of like difficult to understand what the problem is talking about at the very first view of the problem set, but let's look at here. We know that ABC is a triangle, right? We know that D is on BC. I'm not going to draw it right now, but think about this one. Point KA is a conjugate accentroid. What is conjugate accentroid again? Conjugate accentroid is a point that meet with two conjugate external median, right? The intersection point of two conjugate external median, right? So remember that we discussed the property of the conjugate external median. The conjugate external median on one vertex is actually the tangent line of the circumcircle of this triangle that passing through that vertex, right? So we're talking about the conjugate centroid opposite to the vertex A, which means it formed by the conjugate external median on the vertex B and vertex C, which is the tangent point of the circumcircle of triangle ABC, right? If we draw a circumcircle here, right, that's the circumcircle of the triangle ABC. The conjugate external median on point B or on vertex B and vertex C should be perpendicular with OB and OC because it's a tangent line, right? So that means we have the tangent line here and we have a tangent line here. And this point is KA, which is a conjugate accentroid. Okay, it seems that we find the point Ka, that's a conjugate accentroid, and eccentroid that opposite to the vertex A. Now we find this point here, which is actually the tangent line from the vertex B and C to the circumcircle of the triangle ABC. And then it says that AD is a conjugate median if and only if AD, KA are collinear. Basically, it's saying that if we draw the AKA line here and it intersects with BC on point D, this is a conjugate median of the triangle ABC, which is saying that in another form, we have a triangle ABC here, and we find the circumcircle of the triangle. And based on the point B and point C, or vertex B and vertex C, we can find the tangent line that passing through the point B and point C to the circle, to circumcircle, and these two tangent line meet on a point KA. And if we connect AKA here, it meets a segment BC on point D, and we want to prove that AD is a conjugate median of the triangle ABC, which means that we just need to prove that BD to DC equals to AB squared to AC squared. Then it's done, right? So if you remember that in the harmonic bundle, we actually showed this property that if KA, so if we have a, let me just redraw another figure, so we won't touch this one here. In the harmonic bundle video, we discussed about this property. Let's say there is a property, we call it P for now. And if we find two tangent lines from P to the circle O here, and we call this point as A, we call this point as C. If we just draw another line that intersects the circle O on point B and D, then we know that BADC or ABCD is a harmonic quadrilateral, right? We can prove this again here. We want to prove that AB times CD equals to BC times AD, right? And it's obvious that this angle equals to this one, right? Because this is chord with a tangent line, right? This angle equals to this one. And we know this is a common angle, so we know that triangle PBC is similar to triangle PCD, right? PBC is similar to triangle PCD. Similarly, triangle PBA is similar to triangle PAD, right? So based on this, we know that AB to AD equals to PB to PD equals to PB to PD equals to wait, one sec. No, this is not correct. AB to AD equals to PA to PD, which equals to PC to PD, right? Because PA equals to PC, so PC to PD equals to BC to CD, which means AB times CD equals to AD times BC, which means the ABCD is a harmonic quadrilateral. Okay, now if we look back at this one, basically we have the KABC here. That is saying that KA is a point P here, right? That's a two tangent line, and we connect KA to A. So we already know that this point, let's call it E. BE BECA is a harmonic quadrilateral, right? So we know that BECA is a harmonic quadrilateral. And if you remember, still we have this property proved before that in a harmonic quadrilateral, we already know that the diagonal, right? The diagonal intersect the triangles, right? So actually, let me say this way: the diagonal would be the conjugate median of the triangles that are split by another diagonal, right? It seems that the diagonal of AE is a conjugate median of the triangles that's split by another diagonal BC, right? So formed by which means the diagonal AE is a conjugate median of the triangle ABC and the triangle BCE, which is very easy to prove. We want to find the ratio of BD to DC here, right? We want to find the ratio BD to DC. It equals to the area of triangle ABD to the area of triangle ADC, right? And which is half of AB times AD times the sine angle BAD to half of AD times AC times the sine angle DAC, which equals to AB to AC times the sine angle BAD. That is the sine angle BCE, right? Sine angle BCE to sine angle DAC, that is sine angle CBE, which means it equals to AB to AC times, look at sine angle BCE to sine angle CBE, that is BE to CE. Right, and because we already know that ABEC is a harmonic quadrilateral, so we know that BE times AC equals to CE times AB. So BE to CE equals to AB to AC, which means this one equals to AB to AC squared. Right. Similarly, you can prove that ED to DA equals to, actually here I haven't finished yet. So BD to DC equals to AB to AC squared. Right, and it also equals to BE to EC squared. Similarly, you can get that ED to DA equals to BE to BA squared, also equals to EC to CA squared. Okay, so for the theorem 2, we just prove it, right? Because once we have this AKA connect together, intersect with segment BC on a point D, we already proved that this ratio is fixed, right? So once this ratio is fixed, it is a conjugate median. Okay, for the conclusion 2. Conclusion 2, let O be the circumcircle center, which is the circumcenter of the triangle ABC, right? We already have it here. Okay. Let O be the circumcenter of the triangle ABC. Line OM meets the circle of the triangle OBC on point K. The AK is a conjugate median. Actually, I think I forgot to add one point here. M should be the midpoint of the BC. Okay, M should be the midpoint of BC. Right. We already used this in previous cases, but M is the midpoint of BC. So if we connect OM and OM meets the circumcircle of the triangle OBC on a point K, then AK is a conjugate median of triangle ABC. Basically, we want to prove that KA and KA is the same point, right? So let me explain. We connect OM and we extend OM. We meet the OM line with the circumcircle of the triangle OBC on a point K. But if you think about this, then the OM, right? Because this is a OBC and this is a point M, right? And we connect it here because OB equals to OC, right? And we find another point K here. That's on the circumcircle of the triangle OBC, which means the OBCK is a cyclic quadrilateral, right? And we know that OB equals to OC, which means this angle equals to this angle. And because M is a midpoint of BC, so we know that this angle equals to this angle, which means angle OBK equals to 90 degree. Angle OCK equals to 90 degree, right? And if you look at this one and this one, actually this point K is this point KA, right? Because OBKA is 90 degree and OCKA is 90 degrees. That means OBKAC is a cyclic quadrilateral, which means the KA is the point we are looking for. That's the K. So basically it's saying that AK is a conjugate median, which is AKA is a conjugate median. That's a conclusion based on the theorem 2. Okay, so conclusion 3. A cyclic quadrilateral is a harmonic quadrilateral if and only if one diagonal is a conjugate median of the triangle that is from the other diagonal splitting the quadrilateral resulting triangles, right? That's the thing we just proved, right? So the ABEC is a cyclic quadrilateral, right? It could be the harmonic quadrilateral if and only if BD to DC equals to AB squared to AC squared, right? We just proved this. So all of these steps are reversible, so this is true. And conclusion 4. For a certain triangle, any two conjugate external median are concurrent to the third conjugate median, right? This is a triangle. This is a two conjugate external median is concurrent to the third conjugate median, right? It's obviously true. So theorem 3. In triangle ABC, E is on the extension of BC. Find tangent line from E to the circumcircle of triangle ABC. Tangent point is X. AX meet BC on D. Then AE is a conjugate external median if and only if AD is a conjugate median. So let me draw this again. So we want to find the tangent line here. So let's just draw the circumcircle first here. Right. And we have the triangle ABC here. And we know E is a point here, right? A, B, C. This is E, and we find X here. AX meets BC on point D. Right, now we want to prove that AE is a conjugate external medium if and only if AD is a conjugate medium. Okay, so basically what we have here is that we know EX is tangent to circle O. Right, EX is tangent to circle O. And we know that we just can say, okay, if AX or AD is a conjugate medium, we want to prove that AE is an external conjugate external medium, right? So basically our problem set is that if we know BD2, we know that EX is tangent to the circle O, and we know that BD to DC equals to AB squared to AC squared, or, right, I'll just write it down, AB times CX equals to AC times BX, right? Because if AD is a conjugate medium, that means ABXC is a harmonic quadrilateral which has this property, right? So if this is true, then we want to find that BE2CE equals to AB squared to AC squared 2. Right. Okay, how can we get BE2CE? BE2CE equals to the area of triangle BXE to the area of triangle CXE, right? Which equals to half of BX times XE times sine angle BXE to CE, the triangle CXE, which is half of BX times CX times XE, right? So XE. We're talking about the area of triangle CXE. Yes, that is XE times XC times sine angle CXE. Okay. So what is BX? We know that XC cancels. So what is BX to XC? BX to XC can be rewritten as AB to AC, right? Times the sine angle BXE to sine angle CXE. And the angle CXE equals to, because EX is a tangent line, so angle CXE equals to angle CBX. It equals to AB to AC times sine angle CBX to sine angle CXE. Oh, sorry. Should be AB to AC times sine angle BXE to sine angle CBX, right? Because angle CXE equals to angle CBX. So this one equals to AB to AC times sine angle BXE to sine angle CBX, right? That is B to XE, right? B to XE. Right, this is BE to XE, and we want to find that the ratio of the BE to XE here. We want to see if BE to XE. Oh, actually, this is very, we don't need to do this. So it equals to AB to AC times sine angle BXE, right? And BXE equals to this one equals to this one here, actually. So we want to put see here, because this is a tangent line, right? So so actually the sine BXE, let's just extend this tangent line to here. Let's call it point N. The sine BXE equals to sine BXN, right? So sine B angle BXN to sine angle CBX. That's easier. And angle BXN, which is this one, this angle equals to this angle. So the angle BAX. So it equals to AB to AC. Let's write it down here. And sine angle BAX to sine angle CBX, right? And now we can just, because it's sine angle BAX to sine angle CBX, that's actually the ratio of BX to XC, right? So it equals to AB to AC, because we can times the 2R on the numerator and denominator, makes it's 2R times the sine angle BAX, 2R times the sine angle BAX, that is called BX. So BX2, and here it's CX. Right, sine 2R times the sine angle CBX, that's a CX. And we know that BX to CX, right? BX here, BX to CX equals to AB to AC. So it equals to AB to AC squared. And all of these are reversible, which means that we just prove that AE is, if AE is conjugate external median, then AD must be the conjugate median. If AD is a conjugate median, then AE must be the conjugate external median, because this relation keeps the same, right? I mean, BD to DC equals to BE to CE. Okay, let's look at the theorem 4. Theorem 4 is saying that in triangle ABC, D is on B.